So I'm going to jump right in. The title tonight is Climate Change, Causes, Impacts, and the Effect of the Pandemic. Now, I'm going to talk a lot about science before I get to the pandemic part, partly because I like to talk about science. And some of you will have seen some of it before. It's worth going over again. There'll probably be some new things here. I'll try to highlight aspects of the science that are important to the COVID issue. And here's a quick introduction and context. And what I'm showing here is global mean surface temperature of the Earth over the past 5 million years. So 5 million back 5 million years here to the present. Global mean surface temperature of the Earth. Global mean implies averaged over the entire face of the Earth, from pole to pole, all the way around. Surface temperature means over the ocean, the sea surface temperature. Over the land, it means temperature a few meters above the ground, a few meters above the ice. Where do we get this data from? Well, it's proxy data. There's nobody back here measuring this temperature then. We get it from proxy data, and oftentimes it's isotopic analysis, like, for example, the ratio of oxygen 16 to oxygen 18 as captured in ocean sediments or ice cores. And from that, which is highly correlated with global mean surface temperature of the Earth, we can actually recover this record of GMST, global mean surface temperature of the Earth. And what we see here is that beginning with the Pleistocene epoch, about 2 million years ago, the Earth entered into the Ice Age cycles. Now, I'm using the popular term Ice Age here. The downward swings here are actually formally are called glacial periods, and the upward swings are called interglacial periods. But I'm going to use the popular term Ice Age to denote these glacial periods. I'm going to refer to this as the Ice Age cycle. So for the first 1.5 million years or so of the Pleistocene, the Ice Age cycle was a 40,000 year cycle, but for about the past million years, the Ice Age cycle has been a 100,000 year cycle. So why are we talking about ice ages here? We're here to talk about climate change, the COVID and all that. Well, it turns out for the last couple of million years, the Ice Age cycle really has dominated natural climate change. And the climate change we're concerned about occurs against the backdrop of this natural climate change. So we need to understand the natural climate change to understand the human-induced or anthropogenic climate change we're concerned with. Because this climate change is large. These swings from the glacial periods to the interglacial periods are typically in a range of about 4 to 6 degrees centigrade in global mean surface temperature of the Earth. And the climate change we're concerned about since the Industrial Revolution has been about 1.2 degrees C of warming. So these swings are quite large. So we need to understand this. And the question on the table is, do we understand the Ice Age cycle? Do we know what's going on here? Or is it just a big mystery? And the answer is, yes, we absolutely do understand the Ice Age cycle. And in fact, it is driven by variations in the Earth's orbit around the sun and variations in the orientation of the Earth in space. That's what drives the Ice Age cycle. Now, I'm sure you are all aware that the Earth orbits the sun in an ellipse, such that in Northern Hemisphere summer, the Earth is actually farther away from the sun. Northern Hemisphere winter, it's closer to the sun. That's really good for those of us who live in the Northern Hemisphere because that makes our summers cooler and our winters warmer. What you may not be aware of is this ellipse is not stable in time. It fluctuates on a 100,000 year period due to the gravitational force of Jupiter and Saturn acting on the Earth. Now, it's exaggerated in this picture. It's only about 1% change, but it's enough to have a profound impact on the climate. Now, I'm also sure you're aware that the axis of the Earth is inclined relative to the plane that the Earth orbits in. That's, of course, what gives us the seasons. In Northern Hemisphere summer, the North Pole is tilted toward the sun. In Northern Hemisphere winter, the North Pole is tilted away from the sun. But what you may not be aware of is that that tilt is not stable in time. It fluctuates from about 24.5 degrees to about 22.5 degrees on a 41,000 year cycle. And finally, I'm sure you're aware that there's a North Star, that the North Pole points to the North Star. That North Star is called Polaris. But what you may not be aware of is the fact that the Earth wobbles. And that wobble occurs on a 27,000 year period, and it's due to the gravitational force of the sun and the moon acting on the Earth. Now, we've understood for about 100 years that these variations, these orbital variations, drive the Ice Age cycle. Collectively, they're referred to as the Milankovitch cycles. Now, it works like this. When these orbital variations conspire to decrease solar radiation striking the Earth during northern hemisphere summer, that takes us into an ice age. Now, it's these orbital variations that drive the change to the ice age, but there are 3 feedback loops that amplify that change. Without these feedback loops to amplify the change, this forcing wouldn't actually be large enough to cause the ice age cycle. Snow ice feedback, water vapor feedback, CO2 feedback. I'm going to talk about those in more detail later, so I won't delve into them right now, but just be aware of they amplify the effect of these orbital variations, and that's what drives the ice age cycle. And in fact, that's what takes us out of the ice age cycle when the orbital variations conspire to increase solar radiation striking the Earth during northern hemisphere summer. That produces a recovery from the ice age. Why is it northern hemisphere summer? Well, it's because the snow ice feedback operates more strongly, much more strongly in the northern hemisphere rather than the southern hemisphere. Why is that? Because there's a lot more land in the northern hemisphere, so there's a lot more snow and ice on the ground. And also at the North Pole, there's an ocean, the Arctic Ocean, and the melting of the sea ice is a very strong contributor to the snow ice feedback. As the ice melts, the ocean that's left behind is much darker, absorbs a lot more solar radiation. In the southern hemisphere, there's a continent, Antarctica, so you don't get that snow ice feedback nearly as strong. So we've been looking at the 5 million year look here. Now we're going to zoom in way over here and take a look at the 22,000 year look. We're going to be looking back 22,000 years. And it looks like this. Again, we're looking at global mean surface temperature of the Earth over the past, in this case, 22,000 years. And what we see is this low period here is, in fact, the last ice age. And this warming period here is the recovery from the last ice age, driven by the eccentricity cycle. So that means that the Earth's orbit was becoming less like a drawn out ellipse and more like a circle. And that was producing this warming effect. And then there's a cooling trend for about the last 7,000 years. And that's driven by the obliquity cycle. So what's been happening here is the Earth has been losing tilt. In fact, it's lost about 7/10 of a degree of angular tilt over the past 7,000 years. And that's produced this slow cooling trend. For point of reference, 9,000 years ago is generally agreed to be the beginning of human civilization. So that occurred right here. So pretty much all we know, science, art, religion, everything, literature has occurred in this region. Now, there are a couple of other factors that are things that are apparent on this chart. This is called the Younger and Older Dryas period. This is about a 1,500 year interruption in the warming. It had to do with disruption of the ocean's thermal haline circulation due to melting of ice over the continents and fresh water flowing into the ocean. Dryas, by the way, is the name of a flower, a type of flower that flourished in Europe during this period, Dryas occidentala. This is called the medieval warm period, this little bump right here. And this little dip right here is called the Little Ice Age. The Little Ice Age is famous because the River Thames froze over during that period. And finally, we have this red spike. The red spike here is, in fact, the post-industrial global warming that we have been concerned about. Now, there are a couple of things that are apparent in this figure. And the first is that the global warming we're concerned with is going in the wrong direction. Natural climate change has been producing a cooling trend here. And in fact, if left to its own devices without human intervention, the cooling trend would continue for about another 8,000 years, and then it would turn down rapidly, such that we would get to another ice age in about 20,000 years. But in fact, we're going in the opposite direction. And we're going in the opposite direction very fast. In fact, this warming that we've experienced over the past 100 years or so is about 20 times faster than natural climate change. 20 times too fast, going in the wrong direction. Now, I've given this analogy before. Some of you may have heard it, bear with me. Others may have not, it's kind of funny. Here's the deal. Imagine you're a golfer and you're golfing down at Quail Lodge and you take a wrong turn in your golf cart and suddenly you find yourself westbound on Carmel Valley Road. Unfortunately, it's car week, and suddenly you encounter a Lamborghini going the other direction at 200 miles an hour. And by the way, that's not far-fetched, because during car week, I can assure you there are occasionally Lamborghinis going 200 miles an hour on Carmel Valley Road if the cops aren't around. So here's the thing. If natural climate change is you puttering along at 10 miles an hour in the golf cart, what we've been seeing here for the past 100 years is a Lamborghini going 200 miles an hour. Now, you would never confuse a Lamborghini going 200 miles an hour with a golf cart going 10 miles an hour. And that's the thing. That's the difference between this human-induced climate change and natural climate change. It's a big, big difference. 20 times too fast, going in the wrong direction. So we're going to zoom in once again, and now we're looking at the same thing, global mean surface temperature of the Earth from 1850 to 2017, and now from 5 different sources: the Japanese Meteorological Agency, European Center for Medium Range Weather Forecast, the UK Met Office, and two US products, a NASA surface product and a NOAA surface product. Now, some of these temperature analysis products involve satellite data, computer models. Some of them involve only surface data and no computer models. But the point is, they all 5 paint the same picture. 5 independent analyses, 5 independent data sets, all painting the same picture. And the picture is as follows. From 1850 to 1880, not too much going on. From 1880 to 1910, a slow decline. 1910 to 1945, fairly rapid warming. 45 to 75, kind of going sideways, maybe a slight downward trend. And finally, beginning in the mid-70s and extending to the current time, a very rapid upward trend, very strong warming. Notice how closely, particularly in the modern era, these 5 different independent analyses agree. That's because the climate system is very well sampled, oversampled in terms of making the observations to understand climate. Also, notice that it doesn't go up in a straight line. The temperature doesn't go up in a straight line. It's kind of like the stock market. Stock market doesn't go in a straight line. There's volatility. There's volatility here too. And we call this volatility something special. It's called, in fact, climate variability. Climate variability is changes in the surface temperature of the Earth that occur on timescales of months to decades, whereas climate change occurs on scales of 30 years or longer. Climate variability, these ups and downs here, these dips and these peaks and valleys, involves things like El Nino and La Nina, which we're very familiar with here, the Atlantic multi-decadal oscillation, things like that, usually involving the atmosphere and the ocean oscillating together. But they are essentially moving heat around on the Earth, but not causing heat to accumulate on the Earth. Now, climate deniers often seize on this. They'll say, look at this, global warming's over. Never mind this part. Oh, look at this, global warming's over again. Oh, what do you know? Global warming's over, global warming's over, global warming's over. Oh, what do you know? Global warming is over. But in fact, they don't look at the long-term trend. And that's what you really have to look at, the long-term trend. If you're looking at a record that's 30 years or longer, you're looking at climate change. If you're looking at a record that's 20 years or less, you're not looking at climate change, you're looking at climate variability. 20 to 30 year record, that's kind of gray area. But generally speaking, you want to be looking at a record and making decisions based on things that are happening 30 years or longer. 50 years or longer would be even better. Now I'm going to show an animation of one of those products. In fact, this is the NASA product, the NASA Surface Temperature Analysis. And what we're going to be looking at here is temperature anomaly of global mean surface, or of surface temperature of the Earth. Temperature anomaly is just a fancy way of saying temperature difference from a reference field. And in this case, the reference field is the 30-year average of surface temperature from 1951 to 1980. And the temperature scale is shown here, where we're looking at yellows and oranges, it's warmer. In fact, the dark oranges are 2 degrees C warmer than that reference field. The blues are colder, and in the dark blues, in fact, are 2 degrees centigrade colder than that reference field. And I'm going to run this animation. I'll call out the decades, and you just keep focused on the temperature changes. Pay particular attention to what happens in the 70s. The 70s is where the temperature really started to increase. And, you know, we saw that on the previous charts. So here we go. 1880s, 1890s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s, 1970s, 1980s, 1990s, 2000s, 2010s, and we ended up in 2018. So a couple of things are apparent from this. First of all, The land is warming faster than the ocean. Although the ocean is certainly warming, you see all these yellows all around here. In fact, the land is warming about twice as fast as the ocean, even though about 95% of the heat of global warming is going into the ocean. Why is that? Well, that's because the oceans have huge, huge heat capacity compared to the land. In fact, about a factor of 100 greater heat capacity. Heat capacity is the ability to absorb heat while warming up a certain fixed amount. So the oceans have huge heat capacity compared to the land and the atmosphere. The farther you go north, towards the North Pole, the more the warming increases. In fact, the Arctic region is warming about 2 to 3 times faster than the global mean temperature. And that's not a good thing because, of course, we worry about the permafrost melting up there and that releases methane. And of course, the melting of the Greenland ice sheet is contributing to sea level rise. The melting of the mountain glaciers is contributing to sea level rise. Big problem there. Note that it's not warming everywhere. There are some blues here. The big patch of blue right here, a little bit of blue in the middle of the Pacific Ocean, a lot of blue along Antarctica. Generally speaking, the blue areas have to do with changes in ocean circulation. For example, the Gulf Stream circulation has shifted farther offshore here, and the Gulf Stream is also weakened, and that's contributed to this cooling here. So it's not warming everywhere. Notice that in continental United States, the western 1/4 of the US is warming significantly faster than the rest of the United States. Here in California where we live, it's warming significantly faster than, for example, in the southeastern United States. So that's a picture of what's been going on. And so what's causing that? What's going on here? Do we understand what's going on here? And of course, the answer is we do. We absolutely do. In fact, we've understood for about 100 years what's going on here is, in fact, the greenhouse effect. And the greenhouse effect works like this. The Earth is warmed by incoming solar radiation, and it's cooled in 2 ways: by reflected solar radiation, and that's reflected by clouds and aerosols in the atmosphere and reflected from the surface of the Earth, particularly from the snow and ice covered areas because the white surface that reflects is highly reflective. And the Earth is also cooled by outgoing long wave radiation or infrared radiation, radiated from the atmosphere itself, from the tops of clouds, and most importantly, from the surface of the Earth. And then finally, greenhouse gases in the atmosphere trap the outgoing long wave radiation and warm the lower atmosphere and the surface of the Earth, kind of like, you know, putting a blanket on at night. The more you need that blanket because you want to stay warm, but the more blankets you lay on, someone keeps laying blankets on, pretty soon you're going to get too warm. You're going to warm up too fast. And the problem is human activities increase greenhouse gases in the atmosphere and increase the warming. That's analogous to someone piling on those blankets when you're trying to sleep at night. Now, these are the greenhouse gases: water vapor, which we perceive as humidity in the atmosphere; CO2, carbon dioxide; methane; nitrous oxide; and the fluorinated gases, or the F gases. Now, notice I've colored water vapor differently. It turns out that water vapor traps more outgoing long wave radiation than any other greenhouse gas, but it does not drive global warming. And that's why I've colored it differently here. Water vapor does amplify global warming through the water vapor feedback loop we're going to talk about in a second, but it does not drive global warming. Why is that so? That's so because water vapor is in balance with the natural hydrologic cycle. And humans are not putting large amounts of water vapor into the atmosphere. Even if we were, it wouldn't make any difference because the time frame for water vapor in the atmosphere is very short, on the order of days to weeks. There's this process called rain and also snow that will remove that water vapor from the atmosphere if too much starts to build up. It only changes if the natural hydrologic cycle nudges it in a direction of increasing or decreasing. For example, if the ocean is warming, that kind of thing. But the other gases here that are colored in magenta, they are not in balance with any natural cycle. There is a natural carbon cycle, but the CO2 in the atmosphere is way out of balance from the natural carbon cycle because we humans are putting so much CO2 into the atmosphere. Same is true of methane, nitrous oxide, and the fluorinated gases. They're all increasing because they're not in balance with any natural cycle, unlike H2O, unlike water. Now, I mentioned earlier the snow ice feedback effect. It amplifies this global warming we're experiencing. I just want to talk about it in a little more detail. It works like this: increasing global temperatures cause decreasing snow and ice. The snow and ice starts to melt. And what's left behind when the snow and ice melts, for example, over the Arctic Ocean here, is a much darker background. And that increases the sunlight absorbed by the land and sea, which in turn further increases the global temperatures, which decreases the snow. And you keep going around this feedback loop, and it amplifies the warming. Similarly, there is the water vapor feedback effect. Increasing global temperatures increase the evaporation of water from oceans and land, yields increasing water vapor in the atmosphere, which traps more infrared radiation, which in turn increases global temperatures. And again, you go around this feedback loop and you amplify the warming. These feedback loops don't drive the warming, but they amplify the warming, and they're very effective. Taken together, the snow ice feedback effect and the water vapor feedback effect amplify the warming by about a factor of 3. So for example, we've seen 1.2 degrees C warming since the Industrial Revolution. About 0.4 of a degree of that was a direct result of CO2 and other greenhouse gases being put in the atmosphere. But the remaining part was a result of these two feedback effects, which have amplified the warming by a factor of about 3. Now, I know what you're thinking. If I could see the looks on your faces, I can't. But if I did, I know I would see a look on your faces saying, hey, wait a minute, Mike, this must be an unstable situation. It's like taking a ice pick and trying to balance that ice pick on the tip. It's not going to be stable because these positive feedback effects, these are positive feedback effects, which tend to amplify any little change. They will just drive the system unstable. Well, actually, it doesn't, because there is a very powerful negative feedback effect, and that's the long wave radiative feedback effect. And here's the one and only equation in this talk, and that says the outgoing long wave radiation is proportional to the temperature to the 4th power, the temperature of the surface of the Earth to the 4th power. Well, where T is the temperature of the Earth in degrees Kelvin. Degrees Kelvin temperature scale is like the centigrade scale, except 0 is not at the point of freezing water. It's at absolute 0, which is minus 273 degrees centigrade. So what happens here, as the Earth tries to warm up, this equation here, this expression here, increases the outgoing long wave radiation, and increases it very rapidly because of this temperature of the 4th power dependence here. And that increases the cooling. So that tends to decrease global surface temperature. So if the Earth tries to warm up, this tries to cool it back down. Conversely, if the Earth tries to cool down, this will try to warm it back up. So it's a negative feedback effect which tries to stabilize things. Unfortunately, it's not in balance right now because we are forcing things with the emission of these greenhouse gases. But I want to take the opportunity here just to do a quick little thought experiment. It has relevance to what we're going to talk about later on with the pandemic. Suppose we had a magic wand and we were able to suddenly halt the growth of greenhouse gases in the atmosphere and make them stop right where they are right now. So that would require reducing emissions by a factor of about 3, which is a goal to achieve by 2050. Let's say we had a magic wand and could do it instantaneously. It happened, right now. What would happen? Would the Earth start to cool down? Would it stabilize? What would happen? Well, the answer is the Earth would continue to warm. Even if we stabilized greenhouse gases right where they are right now, the Earth would continue to warm for about 20 years, a couple of decades. That's because there's huge inertia in the system and it just doesn't turn on a dime. Now it would be warming at a decreasing rate, and eventually it would stabilize because the long wave radiative feedback effect would bring things into balance. But it would take about 20 years for that to happen. And that's relevant to this COVID discussion because yes, we've had a very big decrease in greenhouse gas emissions over a period of a few months. But it takes 20 years for the atmosphere really to respond to that. And so it's part of the answer that we're going to be looking at later on. Now, everything I've told you so far, that's not just me talking. That is in fact the overwhelming international scientific consensus on this matter, as shown by this partial list of leading science organizations that have made formal declarations confirming human-induced global warming. Everything I've told you is completely consistent with what all of these leading science organizations around the world have been saying for years, including the most prestigious in the US, the US National Academy of Sciences, the US National Research Council, the American Association for the Advancement of Science, and the two organizations that have purview over the atmosphere, the American Meteorological Society and the ocean, the American Geophysical Union. There is an overwhelming international scientific consensus on this matter. It is not in doubt. So let's talk about those greenhouse gases. They are, as I mentioned before, CO2, carbon dioxide, methane, nitrous oxide, and the F gases. And here is a depiction of the contribution of the various greenhouse gases to the current rate of global warming. CO2, carbon dioxide, is the dominant greenhouse gas. It's accounting for about 72% of the current warming, followed by methane, also known as natural gas, the very same natural gas we burn in our homes to heat our water and so forth. Nitrous oxide, product of agriculture mainly from fertilizers. And finally, the fluorinated gases, the F gases, which are used in refrigerants, used in insulation, and used in the production of semiconductors, that kind of thing. It turns out the potency of these gases actually increase as you go down this list. The fluorinated gases are by far the most potent greenhouse gas, but fortunately there isn't much of them in the atmosphere. Carbon dioxide is much less potent than the other gases here, but there's a huge amount of carbon dioxide in the atmosphere. And we're putting a lot of carbon dioxide in the atmosphere every year. This is just a snapshot in time. It doesn't account for the lifetime of the greenhouse gases, but just, in fact, gives us a snapshot of time of what's happening right now. So let's take a look at CO2 in the atmosphere, the dominant greenhouse gas. And here's a depiction of that from 1700 to 2019. And you can see as the Industrial Revolution started to ramp up, particularly in the 1960s here, CO2 increased very dramatically. And the pre-industrial level was about 280 parts per million. Parts per million is the general way we measure this. And now we're well above 400 parts per million. You may have heard the term Keeling curve after the famous Scripps oceanographer, Charles Keeling. He's the first guy who made very detailed measurements of CO2 in the atmosphere. And he was the first to show there was an annual cycle in CO2. It's maximum in the spring, minimum in the fall. Now, a mass of CO2 in the atmosphere is also relevant. It turns out since over this period from 1850 to 2018, human activities have emitted about 2 trillion tons of CO2, not billion, trillion, 2 trillion tons of CO2 in the atmosphere. And about 1.1 trillion tons are still there. We're about 1.1 trillion tons above the pre-industrial level. Imagine what 1 trillion tons of CO2 would look like. And we're currently putting about 40 billion tons of CO2 per year into the atmosphere. So where's that CO2 going, that 40 billion tons per year? Well, about 30% is going into the land. It's being sequestered by plants and trees, particularly the roots of trees. It's being sequestered into the soil. That's what we want. That's really good. About 20% is going into the ocean. That's not so good. It's dissolving into the ocean. That's causing the CO2 levels in the ocean to increase. And that's also causing the ocean to trend more toward the acidic side. We call that ocean acidification. And that has a negative impact on lots of marine life, particularly the larvae of shellfish and coral reefs and so forth. And finally, the remaining 50% roughly is accumulating in the atmosphere. So essentially we're putting CO2 in the atmosphere about twice as fast, two to three times as fast as the natural cycle can take it out. Where's it coming from? Well, globally, by economic sector, it looks like this. The top 3 account for about 2/3 of the emissions. The top 3 are electricity and heat production. That's basically energizing the power grid. Agriculture, forestry, and other land use. That would be land and beef production, deforestation. Industrial production, particularly steel and cement production. And those 3 sectors account for about 2/3 of global emissions. Transportation is actually pretty low on the list here, about 14% globally, followed by petroleum refineries, and finally on-site fossil fuel burning and buildings. That would be heating and cooking with natural gas, for example. So what about by country? Well, here are the top 20 CO2 emitters for the year 2013. I don't think this list has changed very much, so I think the ranking here is probably still pretty much the same. China by far is number 1. US, in terms of total emissions, US is down by a factor of 2 beyond that. But we're well above all 28, now 27 countries of the European Union, followed by India, Russia, and on down the list. Now, another way of looking at this is per capita emission. That's tons per person. So basically, you just take the number of tons of CO2 emitted by a country and divide by the number of people in the country. Well, there's a lot of people in China. They drop pretty far down. And guess what? We're number one. We have the highest per capita emission of CO2 of any country, about 17 tons per person. By the way, per capita emissions in California are only about 11 tons. So 11 compared to 17, we're doing good compared to the US average. It'd be nice to say we're doing really well because, you know, we're really enlightened and green and so forth. And there's probably some truth in that, but also we have much more benign weather here compared to, for example, you know, the states that have to deal with harsh winters. And also our economy is not a smokestack economy, it's more of an information-oriented economy. So we're doing pretty well. But we're not the only ones that have a high per capita. Canada is pretty high, Saudi Arabia is pretty high, Australia is pretty high. So here's where we are now. You know, this is the 22,000 year look, looking back at it. Again, here's where human civilization began, and here this red spike is what we're concerned about. This is where we've warmed since the Industrial Revolution. The question is, where are we going? Well, that depends on what we do, where we are the people of the world. If we follow the most stringent recommendations of the Paris Climate Accord, which means we reduce greenhouse gas emissions by a factor of about 3 between now and 2050 over the next 30 years, and keep on reducing them to pretty close to zero, not all the way to zero, but pretty close to zero. By the end of the century, we would end up here, 1.5 degrees C plus or minus 0.7 degrees C above the pre-industrial level. If we don't do anything, if we in fact adopt what most people refer to as business as usual, which means we just simply forget about this problem, discard the Paris Climate Accord and continue doing business as usual, we're going way up here, 4.5 degrees plus or minus 1 degree. Now look how extreme this is. This is about the change that occurs from an ice age to a warm interglacial period. That's huge. That's huge. The entire history of civilization, this is how much change we've seen, you know, about less than 0.5 degree centigrade of cooling. And now suddenly we're going to go up here. That would be just devastating. Well, I don't think we're going up here, but I'm also pretty confident we're not going down here. We are not currently on track to hit the 1.5 degrees C target by the end of the century. We're going to end up somewhere in the middle is my prediction, and probably maybe halfway in the middle, maybe 3 degrees. And that's pretty darn extreme when you take a look at this. So what are the consequences of this warming and these climate change? Well, I'd like to divide the consequences into 2 categories: natural consequences, that would be consequences in the natural world, and human consequences. So here's what we can expect. In fact, here's what we were seeing: increasing temperature of the land, ocean, lower troposphere. Now the troposphere is the lowest layer of the atmosphere where the weather is, from the surface up to about 40,000 feet. It's only the lower troposphere that's warming. Surface up to about 20,000 feet. When you're going up to altitude on an airline flight, when you're about halfway up to cruising altitude, that's the lower troposphere. That's the only part that's warming. Every place above that is actually cooling. And what does that do? Well, that makes the atmosphere more unstable because you're warming it from below and cooling it from above. Warm air rises, and in fact, that warm air rising is a big source of energy for storms. So what we're seeing and expecting, and just good common sense, increasing frequency and intensity of severe storms, increasing frequency of life-threatening heat waves. At the same time, there's an increase in the water content of the air. As the air gets warmer around the world, it can hold more moisture. And so we're seeing an increase in the absolute humidity. That's the water content of the air. And that's leading to an increasing frequency and intensity of floods in wet regions, in regions that have no trouble forming rainfall. When they do have rainfall, it's even more intense than normal. So that leads to increasing frequency and intensity of floods in wet regions. But we're also, even though the water vapor in the air is going up, we're seeing a decrease in relative humidity. Relative humidity is how much, it tells you how much, how close you are to 100%, how close you are to saturation forming rain. And you hear on the news all the time, you know, the relative humidity is is 70% or 50%. In dry areas, like where we live, it's hard to get to 100% humidity up at the cloud level. And you have to do that, of course, to create rain. And that's why we don't have a whole lot of rain here. Well, unfortunately, the relative humidity is going down. And that means that increasing frequency of droughts and wildfires in dry regions like where we live. Also, as the atmosphere warms, decreasing snowfall relative to rainfall. As the air is warmer, precipitation's falling, melts, becomes rainfall rather than snowfall. Not so good, because particularly for us here in California, because that produces decreasing mountain snowpacks, and also the warming produces earlier snow melt. Big issue for California, because as you know, the snowpack in the Sierras is a big source of our water in the dry season, and that snowpack is going to be decreasing. In fact, it has been decreasing. Melting of ice sheets and glaciers producing, of course, rising sea levels. Decreasing pH of seawater, that's ocean acidification. Decreasing oxygen levels in the ocean as the water warms. And together these produce increasing mortality of coral reefs, coral bleaching. I think it's about 20% of the world's coral reefs have already died, and pretty much all the coral reefs are under stress, including the Great Barrier Reef in Australia, the world's largest living structure. Decreasing productivity of fisheries, a very significant portion of fisheries, even in away from the tropics, depend on coral reefs in one way or another. And finally, increasing species migrations and extinctions with loss of biodiversity. Now, I've highlighted this loss of biodiversity here because that is a significant issue actually relative to the COVID pandemic. And I'll talk a little bit more about that later on, but just briefly, biodiversity in natural habitats is an important stabilizing effect. And when you start to lose biodiversity, a couple of things happen. It makes it more likely that diseases will form in that natural habitat, for example, coronaviruses. And it makes it more likely that those diseases will spread to human populations, particularly as humans encroach upon those wildlife areas. Now, I'll throw out an example I think we can all kind of understand on that. When we have periods of drought, as you know, it's not unusual to see raccoons in your neighborhood. They're coming out of the forest, they're looking for water, looking for food. Well, you know, raccoons carry rabies, and that is the, you know, that increases the likelihood of transmission of that disease from the animal kingdom to humans. That's just one example. There are many other examples when stresses such as drought stress and heat stress affect natural habitats, that puts wildlife under stress, that increases the possibility of diseases flourishing in those environments, increases the possibility those diseases will spread to humans. Now, I'm not saying that climate change has caused COVID-19 to happen. We don't even know for sure where it came from. Probably came from bats, but I don't know that's been completely pinned down yet. But I wouldn't be surprised later on when everything is studied and figured out if there wasn't some climate change component to this whole thing. I'm not predicting that, but I'm saying I wouldn't be surprised if it does turn out that way. And just want to show a couple slides here on some of the things we've talked about. This is showing the trends of severe storms, severe floods, heat waves, droughts, and wildfires from 1980 to 2010. You can see there's a clear upward trend on all of these weather phenomena. Here's a depiction of global mean sea level rise from 1900 to 2015. And you can see the sea level is increasing. It's gained about 8 inches from 1900 to 2015. But a couple of things are apparent here. The most important one is the fact that it's accelerating. Notice the upward curvature here. Sea level rise is accelerating. A couple of things I want to just quickly throw out about sea level rise. Number one, it's accelerating. Number two, it's typically been underpredicted by the models. Current predictions are for global mean sea level rise to go up by about 1 meter by the end of this century. But it wouldn't be inconceivable that it's 2 meters, because very typically the models are under predicting sea level rise, and they have to be continually revised upward. Number three, sea level rise is not globally uniform. It doesn't go up the same everywhere. There are other, in fact, it varies by a factor of about 3. There are parts of the world where sea level is rising 3 times faster than the global mean. Why is that? Well, it's because the ocean circulation is changing, and it has a profound impact on sea level rise. And in fact, some of the areas that are most threatened by sea level rise, islands in the tropical Western Pacific are in a region where the sea level is in fact rising the fastest. Here in California, we're pretty much on track to increase at about the rate of the global mean. So we're not going to be significantly above or below the global mean rate of sea level rise, which is a good thing. And then finally, and by the way, after 2050 is when we have to be really concerned. But around 2050 is when the Antarctic ice sheet starts to really play a role in sea level rise. And that's when things are probably going to really accelerate. And then finally, the final thing I want to quickly throw out is there is a very, very long time lag between warming Earth and rising sea level. So you might think, gosh, if we can just stabilize this temperature by the year 2100, then we'll be good. We can live with that and everything's good. Well, the fact of the matter is the sea level is going to continue to rise. It's going to continue to rise for many centuries, maybe as long as 500 to 1,000 years beyond that time, even though we stabilize the temperature of the Earth. Why is that? Because basically it takes that long for all the ice that's going to melt to actually melt. It takes hundreds of years, maybe even as long as 1,000 years, for the ice sheets to come into equilibrium with the warming temperature. So what that means is future generations beyond the end of this century are actually going to have to bring the temperature down if you don't want to see the sea level continue to rise. And in fact, it would in fact rise by tens of meters over the period of 500 to 1,000 years. So future generations are going to have to deal with that. So finally, human consequences of a warming world. Well, increasing economic costs resulting from increasing frequency and intensity of weather events, increasing prevalence of wildfires, big issue for us here, and rising sea levels. Increasing competition among nations for water and food caused by increasing drought and decreasing agricultural and fisheries production. And by the way, the fisheries production of California, it will be impacted in a negative way. Increasing displacements of people and unrest in populations susceptible to recruitment by violent extremist groups caused by all of these stresses. Increasing human mortality from heat waves. By the way, heat waves kill more people globally than any other weather phenomenon. You worry about tornadoes, typhoons, and hurricanes, it's heat waves. Heat waves kill more people than anything else. Increasing threats to human health as tropical diseases spread into higher latitudes, and reduced biodiversity increases the likelihood that diseases will jump from animals to humans. And as I mentioned before, I wouldn't be at all surprised if when all is said and done and all the studies are done, that in fact climate change may have played a role in increasing the probability that the coronavirus would in fact jump to the human population. And finally, risks are unevenly distributed between groups of people and between regions. Risks are generally greater for disadvantaged people living in developing countries, partly because of the fact they simply don't have the resources to deal and to adapt to the climate change. Okay, that's all prelude to now here's the thing you might be most interested in, impact of the COVID-19 pandemic on climate change. Well, the economic fallout from the pandemic has produced the largest drop in global energy demand since the Great Depression of the 30s. This drop has translated directly into a drop in global CO2 emissions. If some restrictions on economic activity stay in place worldwide until the end of the year, which is likely, then global CO2 emissions will likely drop by about 7%, which is 6 to 10 times larger than during the 2008 global recession. China has been responsible for the biggest drop in CO2 emissions, followed by the US, Europe, and India. So the question is the fall off in CO2 emissions caused ultimately by the pandemic a silver lining that will help the world achieve the goals of the Paris Climate Accord? It'd be nice if it was. We would think, gosh, as bad as this thing has been, at least there's a good part to it here, a silver lining. So that's the question on the table here. And to address that, I want to take a look at this figure right here, which is global CO2 emissions by year. Now, this is not CO2 in the atmosphere. We looked at that Keeling curve, which was the actual amount of CO2 in the atmosphere. This is not what we're looking at here. What we're looking at here are global CO2 emissions by year. So how much are we actually putting into the atmosphere right now? So you can see that beginning, it was slowly going up here, and then beginning, right about the end of World War II, it really ramped up and it's been climbing pretty fast here. You can see the effect of the Great Depression right here. You can see end of World War II. These are the first and second oil shock, collapse of the Soviet Union. This is the financial crash of 2008. And here's where we're going to be by the end of 2020. This is a pretty big jump. We've gone from here down to there, which is significantly larger than, the Great Depression. So the question is, is this going to put us on a track where we need to be? Well, this is where we actually need to be in 2050. If we want to achieve that Paris Climate Accord goal of holding warming to 1.5 degrees centigrade above pre-industrial by the end of this century, we need to be down here, which is basically back to about 1960s level, reducing by a factor of about 3, and then we need to keep on going. We need to keep on going. So the question is the fall off in emissions a silver line that will help achieve the goals of the Paris Climate Accord? Can we sustain this downward trajectory such that we hit this target here of about a factor of 3 reduction by 2050 and ultimately end up by the end of the century out here at 2050, pretty close to zero, not gonna be come all the way to zero, but pretty close to zero. Is the pandemic and this huge pullback in economic activity, is it something that will put us on this track here? Well, let's take a look at that. On the positive side, many see the efforts to contain the economic fallout of the pandemic as an opportunity to accelerate the shift to cleaner energy alternatives. Options could include ensuring that economic stimulus programs prioritize investments in cleaner energy or conditioning assistance to businesses, especially in carbon-intensive sectors, on drastic cuts in emissions. Similarly, financial industry bailouts could require banks to invest less in fossil fuel and more in climate change mitigation and resilience efforts. Prospects for a green stimulus and recovery are promising in Europe, which could provide an example for the rest of the world. For example, in response to a call to abandon climate measures, an EU spokesperson was categorical and said, quote, "While our immediate focus is on combating COVID-19, our work on delivering the European Green Deal continues. The climate crisis is still a reality and necessitates our continued attention and efforts." On the negative side, in the US, congressional Democrats pushed for measures that would accelerate the shift to renewable energy alternatives when negotiating the recent stimulus package, but President Trump threatened a veto and the proposed measures did not survive. In the US, after the oil lobby petitioned the Trump administration to relax enforcement, EPA said it would not penalize companies that failed to comply with federal monitoring or reporting requirements if they could attribute their noncompliance to the pandemic. And in recent days, EPA announced a rollback on car emission rules that were a central piece of US efforts to reduce greenhouse gas emissions. In the US, some fossil fuel firms have been determined to pursue government bailouts without strings binding them to a less polluting future. This tweet speaks for itself. "We will never let the great US oil and gas industry down. I've instructed the Secretary of Energy and the Secretary of the Treasury to formulate a plan which will make funds available so that these very important companies and jobs will be secured long into the future." Continuing on the negative side, the European Union has come under pressure to shelve crucial climate initiatives, with Poland calling for a carbon trading program to be put on hold, and the Czech Republic urging that the EU's landmark climate bill be abandoned, while airline companies have pressed regulators to delay emissions cutting policies. China has already announced delays in climate change programs, extending deadlines for companies to meet environmental standards, and postponing an auction for the right to build several huge solar farms. China has accelerated its building of coal-fired power plants, approving in the first 3 weeks of March 2020 the equivalent of 7,960 megawatts of new coal-fired plants, the dirtiest burning plants, which was more than the number agreed to in the whole of 2019. In Brazil, the Federal Environmental Agency announced it is cutting back on its enforcement duties, which include protecting the Amazon from accelerating deforestation, a real crime, that could lead to the release of massive amounts of greenhouse gases that are stored in one of the world's most important carbon sinks. Continuing on the negative side, reducing greenhouse gas emissions to the levels required to halt and eventually reverse climate change will require significant investments. In fact, about 1% of global GDP every year for the next 30 years. Now that's based on something some of you may be familiar with. That's the Project Drawdown information, drawdown.org. I highly recommend drawdown.org if you're not familiar with it. They've recently come out with a new updated version of their analysis, and it talks about 2 scenarios. We'll get to that in a second. But essentially, there's a lot of money required up front, about 1% of global GDP over the next 30 years. And for cash-strapped governments, including our own government, saddled with tremendous debt from stimulus spending, it's going to be hard, that much harder to find these needed investments in climate change programs. Basically, as the world struggles to recover economically and with a glut of low-priced oil available, there will be tremendous temptation to forge ahead with heavy fossil fuel usage as a quick and cheap way to revive economies. You may have seen a while back pictures of those oil tankers that were queued up off of Long Beach. They had no place to offload their oil. They're just being used as very expensive storage tanks. There was a period of time a couple months ago when the price of oil went negative. That means you had a bunch of oil in your hands. You had to pay people to take it off your hands because it was difficult to store and nobody wanted to buy it. So that means the price of oil is low. There's a glut of oil out there, and it's going to be very tempting to burn it to produce a cheap source of energy to help recover. I mentioned Project Drawdown. Their latest version of their analysis talks about two different scenarios. Scenario one is hold global warming to 2 degrees centigrade by the end of this century. That's probably doable. Scenario two is hold it to 1.5 degrees centigrade. I think we're already beyond the point where that's achievable. For scenario one, the 30-year cost of the world is about $23 trillion. That's about 1% of global GDP. Scenario two would be about 30 trillion, 1.25% of global GDP. But there's a cost savings here. That's the good news. You invest 23 trillion up front, but you save 79 trillion or 95 trillion return on investment. For scenario two, it's 30 up front to get a return on investment is 145. And here are the numbers for the US. So it's going to be tough. It's going to be tough to convince governments that they have to make these investments when we're recovering from such a serious global recession. Where's this money going to come from? Well, according to the International Monetary Fund, the IMF, the global fossil fuel industry is currently subsidized at about 5.2 trillion per year, or about 6.5% of global GDP. We're only asking for about 1.25% investment. So there's plenty of room there, quite frankly. If you reduce these subsidies to the oil companies, the fossil fuel industry, there's plenty of room there. Same is true in the US. Again, according to the IMF, the US fossil fuel industry is currently subsidized at about 650 billion per year. We're talking about an investment of 190 to 250 billion per year. So there's plenty of room there. What's the deal on these subsidies? Well, in fact, they are tax breaks. They are heavily ingrained into the tax code. They are supported by an army of well-paid and highly effective lobbyists in DC. So it's very, very, very difficult to deal with this. But ultimately, I think that's where we need to go because we need to find the money to make these investments. Continuing on the negative side, the UN's annual climate summit, which was scheduled to take place in Glasgow in November, was postponed until sometime next year as a result of the pandemic. Other international meetings related to climate, on biodiversity and oceans, for example, have also been postponed. While the need to mobilize governments to act on climate has never been more urgent, the inability to gather world leaders to address the issue could make it all that much more difficult to do so. So in summary, is there a climate change silver lining to the COVID-19 pandemic? My answer is no. It's just my opinion. In my opinion, the negatives outweigh the positives as discussed on the prior slides. And history provides a clue as well. In the initial aftermath of the global financial crisis of 2008, for example, global CO2 emissions decreased by 1.25%, only to rise by 5.9% in 2010 as the planet continued to warm at an alarming rate. So I conclude that after the pandemic is over, we will be right back where we were before, or perhaps even worse off, as governments struggle with heavy debt and pressure to put people back to work quickly. Investment in dealing with climate change may fall to lower priority. So what can you do? A few closing comments here. Well, of course, you can learn the basics of the science behind why our planet is warming and the climate is changing. And suffering through my science presentation tonight is a good step on that. And of course, a lot of you have suffered through prior presentations of mine as well. All good. You can do what you can to reduce your carbon footprint while still living the life you want to live. You can join an advocacy group like our group, Citizens Climate Lobby, and participate actively. Whenever you have an opportunity to interact with a leader in your community, be they political or otherwise, let them know that you want to see action taken on this issue. And of course, we CCLers have been very active in that area and engaging with Jimmy Panetta and others. Become a leader in your community on this issue. Many of you are, of course, already are leaders on this issue. And finally, vote for candidates who will address your concerns about climate change. Well, that's it. And what I'm going to do now is I'm going to stop the share here and go back to FaceView and take questions, and hopefully you have some discussion. Who wants to start? Gonna need to unmute yourself.
Hey, Mike, I had a question.
Hi, Lee. Yeah.
Oh, this is William.
Oh, William. Sorry, I was looking at Lee. Hi, William.
Yeah, I was curious on the slide kind of halfway through about the increases in temperature worldwide. The Western U.S.
Yes.
is warming at a faster rate than the Eastern U.S. Can you just tell us about that a little bit? Why is that? Well,
you know, I think mainly has to do with the fact that the Western U.S. is drier, and of course it kind of goes hand in glove, the drying and the rising temperatures. I think that's part of it. Other than that, I don't have a real clear explanation on that.
Thank you.
Mike?
Yes.
It's Lee.
Okay, hi, Lee.
Hi. So I was interested in your description of some of the reflective principles, in part being from our ground level, but also part being from up at like cloud level and whatnot.
Right.
Obviously, there's always risk in tinkering with nature and everything, but I'm wondering if there's any scientific study about anything we could do at that cloud level, introducing, for example, some chemicals that wouldn't have a bad effect, but which would increase that reflective principle to keep more of the heat from reaching Earth.
Yeah, that's a great question. Let me just talk about it more in general terms first. There's been a lot made about the fact that, because of the pandemic, all the cars were shut down and the airlines weren't flying. And very quickly, we saw skies clearing. There were lots of stories about Paris is looking really great. In India, they can see the Himalayas for the first time. And you might want to think, well, gosh, that must mean we're really, greenhouse gases are doing better as well. There's two different phenomena here. There's the greenhouse gases, which in fact are gases, and there's aerosols in the atmosphere, pollution, which are in fact particulate matter. And when you stop putting the particulate matter, the aerosols in the atmosphere, they settle out very fast. The time scale for pollution to settle out of the atmosphere is on the order of weeks. And so pretty quickly, the sky's cleared and that was all good. But in fact, the sky's clearing is actually contributing to warming of the Earth, as you mentioned, Lee, because there's less reflection happening. So in fact, the clearing skies is actually producing a warming effect. Not saying we want to put a bunch of pollution in the air. There's reasons to not have pollution in the air, health reasons, of course. But the fact of the matter is, it's important to understand there are two different time scales here. There's the time scale of air pollution, which is on the order of weeks. There's the time scale of greenhouse gases, which is centuries to even longer. The time scale, the nominal lifetime of CO2 in the atmosphere is about 100 years. Nominal lifetime of methane is about 10 years. Nominal time for air pollution, aerosols like we're talking about, is about 2 weeks. So big issues there. So your question you raised, Lee, was what about using something like putting particulate matter in the atmosphere to increase the reflection? That kind of falls into the general category of geoengineering. There's a lot of different things that have been proposed with regard to geoengineering that might be helpful to increase reflection of solar radiation and decrease the warming of the Earth. Well, generally speaking, I'm saying I think it's great for people to look at that, do that kind of research. But in general, most geoengineering kind of solutions, you got to worry about unintended consequences. You got to worry about side effects of that. If you put particulate matter into the atmosphere, it's eventually going to settle out. Even volcanic ash, which gets way up into the stratosphere, it only lasts for about 2 years and then it settles out. But also you got to worry about the health effects, because you're talking about small particles that can get in people's lungs and have all kinds of impacts in terms of health and ecosystems and so forth. So I'm not optimistic that we're going to really find any solutions along those lines. I think the best solutions have to do with stopping deforestation and pursuing afforestation. We put forests where they weren't there before, those kinds of things. But we have to be, I'm not saying that people shouldn't be looking into these kinds of ideas, but generally speaking, you got to worry about geoengineering solutions having side effects that can be unexpected and negative.
Thanks.
Mm-hmm.
Mike, we have a question in the chat from
Okay.
Vicki. Maybe she could ask it herself. Here.
Can I,
Vicki, are you there?
you want me to read it?
Could, or Vicki could tell it. Wherever
Okay.
you're speaking.
I'll read it. It says, is this the question from Vicki?
Yes.
It says, given that post-election Republicans will be very right-wing, is it realistic for CCL to continue our policy of one-to-one members in the two parties in congressional committees? That would be a great question for Jimmy Panetta. I think if Jimmy Panetta was on the line here, he would say it's always worthwhile to try to work across the aisle and try to find members of their party that I can work with, and we'll come around to our viewpoint. I think probably need to do that. But the upcoming election is huge. There's no doubt about that. It's going to be huge for climate. The outcome of the presidential contest and the outcome of the Senate are absolutely huge in terms of what's going to be possible to achieve in terms of where we need to go. I don't like to usually want to get too political in these kind of presentations, but the election is going to be huge. There's no doubt about that. I think our guy, Jimmy Panetta, will find a way to work with whoever he can to try to make progress on this issue. Who else?
Anybody else with a question? Unmute yourself.
Mike, this is Mary Bell.
Hi, Maribel.
I wanted to go back to what Vicki was asking. We're fortunate in our district that we have somebody who's pretty sympathetic to the cause, but there are other CCLs throughout the country that do work with Republican members of Congress, and they are having good success with the one-on-one dialogue.
Good. Yeah, I think what's one thing that's happening is the public is coming around. You may have heard me talk before about on climate denial. There's a well-funded, well-established climate denial community out there. They're funded by the oil and gas industry to the tune of about $1 billion a year. There's about 100 institutions, think tanks, and research labs, quote unquote, that are funded by the oil and gas industry. And their job over the last 20 or 30 years has been to try to create doubt about the science in the general public. And that doubt has affected the general public. And when you have doubt in the general public, that translates into doubt in legislatures. And that basically slows action down. But they are failing. I mean, the trend is going in a positive way. If you look at the polling, there's been a steady upward trend in people in the general public who have understood that climate change is happening, climate change is caused by humans, and climate change is serious. It's going to impact us in a negative way. The polling results show those trends are upward. So they're losing the battle. They're losing the battle the same way that the tobacco industry ultimately lost the battle over tobacco. And comparison with the climate denial community is to what went on with the tobacco industry back in the 60s and 70s is a completely perfect analogy. Because indeed, some of the same PR firms that are supporting climate denial now were engaged by the tobacco industry back in those years to try to create doubt about the science that said smoking is bad for you. But what they are doing is they are fighting a delaying action. Essentially, they're slowing action down, which is unfortunate. Ultimately, they're going to lose. They're going to lose just as the tobacco industry lost, because more and more people are getting it, particularly the younger generation, particularly the millennial generation, they're getting it. That will translate into people getting elected to Congress and to the Senate that will be motivated to work on this problem. So ultimately, they will lose. But unfortunately, they are creating delay. They're fighting a delaying action to try to stop the ultimate legislation required to address these problems, and that's unfortunate. Who else?
Oh, did you put me off?
No, you're mute. Go ahead.
I think one of the best slides, or best examples for anybody who needs to be convinced that global warming is human caused is the slide you showed where the dot is below the trajectory. And hopefully that's going to be used by people talking to congressional members who want to deny that. I mean, that's just as dramatic as you could imagine.
Yeah, fortunately, I think the hardcore climate deniers, I think they're going down. They're becoming less and less of a factor. But at the same time, there is this sort of delaying action, which is delaying the needed action. But the good news here is the trends are going in the right direction. The trends in terms of public opinion and the feeling in Congress is going in the right direction. We've got a problem in the White House. We've got a problem in the Senate, but the House is, moving forward and has done a lot of things with regard to climate. If we can turn things around in the White House and in the Senate, then we'll be poised to make a lot of good progress.
It's Mary Bell again. The problem is that the last IPCC report said that we have about 10 years now. It was 12 years at the time, but about 10 years to start reversing or rewinding the whole carbon emissions issue.
Yeah, they've been coming out, the IPCC comes out with, I think it's every year they come out with an assessment report. And the last couple of years, they've basically been kind of giving a report card on how well we're doing with regard to trying to achieve the Paris Accord goals. And we're falling behind. That's why I say we're not going to get to 1.5. I think that's off the table right now. We're definitely not on track to achieve that. I think it'll be tough to get to 2 degrees, but I think that's probably doable. Most likely it's going to be more than 2 degrees. And the fact of the matter is you're quite right, Maribel, when you say rewinding, because ultimately we can't just stabilize things there. We've got to start bringing the temperature of the Earth down. And the reason why we need to do that is, well, we either need to do that or we got to start building our cities up because, as I mentioned before, 500 to 1,000 years from now, the sea level is going to be about 30 meters above where it is now. How do we know that? Well, forget about computer models, no computer models here. We know that because the geologists can go back in the historical record through many ice ages, and they can find periods of time, periods of interglacial periods that were about the temperature we're at now. They can find periods where it was warmer than we're at now. And they can also figure out where the sea level ultimately got during that period of time. And when you take a look at that, you see that if we, get to a couple degrees above where we're, 1.5 degrees, whatever, 3 degrees where we're above where, kind of where we're going right now, and we stay there and wait 500 to 1,000 years, the sea level is going to rise about 30 meters because that's how long it takes for the ice sheets, all the ice that's going to melt in the ice sheets to ultimately melt. So, a good question is, can human civilization adapt over a 500 to 1,000 year period to a 30-meter sea level rise? And I don't know the answer to that. I don't know. Maybe it can. I think it would be tough, but that's a long period of time. Maybe it can. And it kind of underscores a lot of what climate change is all about. You got to think long term. You got to think long term. I mentioned earlier, 30-year record is really this sort of the entry level looking at climate change. You need to be looking at 30 years or longer. Well, most people's professional career is about 30 years. That's a whole professional career, and longer is what you have to look at. You have to think long term. You have to think about future generations, and you have to ask yourself 2 fundamental questions. Do I care about the fate of future generations? And number 2, do I care what future generations are going to think about us? When they look back 100 years from now and say, gosh, you people in the 21st century, why didn't you just address this problem? Why did you leave it off to us? Why didn't you address it when it would have been much easier to address than what we have to deal with now? So I hope the answer to both those questions is yes. And I think those are the kind of questions we need to pose to people and to the general public and to our legislators.
One last question from me.
Okay.
Could you talk a little bit about carbon capture, that technology?
Yeah, there was a bill passed a couple of years ago It was, and I can't remember the name of it. And it was actually it was a bipartisan bill that the Republicans supported, because the idea there was we were going to employ carbon capture technology at at production sites, and then we're going to pipe that CO2 down into the earth. That's all good. That's the good part. That's the green part of it. We're also going to build, by the way, a pipeline infrastructure, which is good because that allows us to move that CO2 around, and that stuff is going forward. The bad part of that is the part that got the oil industry on board and got the Republicans to support it was they were going to use that piping of the CO2 down into the ground to actually recover more oil by pumping it down into oil reserves and use that as a way to bring up more oil. And of course, that oil would ultimately burn, and just you're still dealing with the same problem. I'm not terribly optimistic about the carbon capture technology. I'm much more optimistic about moving to green energy, moving to wind and solar. And that's the thing I'm most optimistic about. The fact that that technology is getting cheaper and cheaper, particularly on the solar side, but also the wind turbines are becoming more efficient. They're being deployed more widely. Farmers love them, ranchers love them. It's happening all over the country, and that's all good. And I'm also really more interested in seeing things like Drawdown.org talks about with regard to restoring forests, restoring and protecting peatlands, using the natural world to try to capture carbon, changing the way we do agriculture, moving towards regenerative agriculture, and those kinds of things, to use natural forces to try to capture the carbon. I think that's where we need to go. Highly recommend Drawdown.org. A lot of thought has gone into that, a lot of good science, a lot of good economics, and I strongly recommend taking the time to look through that.
Mike, one last question from me.
Okay.
What I worry about is the melting ice,
Yes.
because it seems no matter at this point, so much is in place making that happen that even some dramatic changes would not slow the ice melting much. Is that true? Are we going to lose all the ice no matter what we do now?
There have been periods of time in the past when all the ice was gone. There's been a number of times in the past where the Earth has been warm enough such that all the ice was melted, and the sea level was about 110 meters above where it is now. Imagine that, 110 meters. I'd be here in Slinsdale, and there was no ice. And in fact, there were crocodile-like creatures living in the Arctic. The rainforests extend all over the Arctic. Those are called hot house periods of Earth. I don't think we're going there again, but yes, the ice is going to continue to melt until we're able to reduce the temperature back down. Most of the sea level rise that's occurred to date has been a result of thermal expansion of the ocean. As the ocean warms, the water expands, and that's driven most of the sea level rise. But the melting glaciers and the melting of the Greenland ice sheet has really kicked in the second half of the century, of the 20th century. The real concern is the Antarctic ice sheet, the east and west Antarctic ice sheets, which hold the most fresh water in the world by far. And they haven't really contributed much so far, but the expectation is they're going to really start contributing to sea level rise beginning about 2050. And that's a real concern. And what happens there, the ice is flowing, the ice sheet actually flows towards the ocean, and the ocean water below is warm, causes it to melt, and some of that water is getting up under the ice sheet, which is accelerating that flow. The science is not well understood. The science of ice sheets is not terribly well understood. Generally speaking, the modeling has been overly conservative, and that's why the models have continually had to be revised upward in terms of sea level rise. But yes, that is a real concern. It's not going to, quite frankly, affect any of us unless expect to live another 400 or 500 years. But yeah, eventually, sea level rise is going to become, unless we're able to begin cooling the Earth back down, then it's going to become a real issue. And as I said earlier, question on the table is, can civilization deal with a 30 meter sea level rise over a period of 500 to 1,000 years? I don't know. That's a good question. I don't know. I will say we in California are pretty lucky. We have a lot of high ground to retreat to, but my home state of Florida does not have that option. And state of Louisiana, for example, which is ground zero for climate change or sea level rise, does not have that option. There's lots of places in the country that don't have the options we have. And even in California, there are cities like San Francisco that are going to be in dire straits.
Well, anybody else on this happy note? But Lee.
Oh, no, I was adjusting my glasses, sorry.
It made your picture get bigger when you did that.
Before we leave, let me say I appreciate everyone coming on tonight and your attention, all the great questions and discussion. I just want to throw out that we're going to have another one of these a month from now on September 9th. Same time, same place. And the speaker will be George Lockwood. He's a resident of Carmel Valley, and it turns out he's a retired gentleman, and he's one of the world's leaders in aquaculture. And he has some great ideas of how aquaculture can play a role in addressing climate change, particularly by helping bring down the CO2 that resides in the ocean. So I think it's going to be a really good talk. So I'm recommending everyone stay tuned for that one. It'll be September 9th.
Great. Well,
Mike, thanks so much. This was fabulous.
Yeah, Mike, this is Dave Rappert. Really good information and nice presentation. And
Oh,
thanks.
thank you.
Thank
Absolutely.
you so much
Thank
for
you, Mike.
this wonderful
coming.
information.
All right. Thanks, everyone.